So shall I start? Okay. Hello everyone, I'm Waleed Shakir and I'm going to present my master's thesis work, which is robot-based incremental sheet forming, trajectory optimization and error compensation. This work is under supervision of Professor Alexander Klepshy. So the structure of this presentation is as follows. I will first give an introduction about the incremental sheet forming, then the problem statement and my research questions and my contribution. Then I will go through the literature review and the methodology. So to start, basically what is the incremental sheet forming? Incremental sheet forming is an innovative flexible process in which you apply progressive and localized plastic deformation in a sheet surface to make certain shape. In contrast to the conventional deep drawing methods like stamping or drawing, this method has a lot of advantages such as the enhanced material formability and the ability to produce complex 3D shapes and the cost reduction, because basically you don't need to design a die for each shape. It has two different types, which is the single point incremental forming and the double-sided incremental forming, which is basically a co-manipulation system. So this work is dedicated to the single point incremental forming, and to understand more about the process, we can see this demo. So this is how the process works. You apply a progressive overload on the sheet to make some deformation and have the final shape. So I think it's enough, so we can go through the presentation. Okay. Although this process has a lot of advantages, it experiences some limitation, which is basically the irregularities, the geometrical inaccuracies, which is presented in figure 4. So the base of the sheet suffer from a pillow effect, which is the tendency of the base to counteract towards the center, and there's also bending at the clamped edge, and also the spring back effect, which is the critical point, disadvantages in this process. And the spring back effect, after you remove the deformation tool, the sheet tries to elastically deform back out from the desired shape, which make like an error between the desired shape and the obtained shape. There's also another part of the problems in this process, which is the using of the industrial serial manipulators that is prone to accumulated error due to the low stiffness, which makes some tool-based deviations. I formulated the problem statement as follows. Like I split the problem into two main issues. The first issue is related to the material itself, which is characterized by the spring back effect. And the second issue is related to the robot itself, which is the tool-based deviation. About that, I formulated my research questions as follows. The first one is, what are the existing solutions employed in the incremental sheet forming, the limitations and the shortcomings? And the second one, how can the material spring back effect be quantified and characterized to mitigate its impact on the desired shape? And the third one, how can the tool-based deviation introduced by the serial manipulators be compensated? So the main contributions of this work, the first one is introducing an effective spring back compensation model, which is a novel stiffness, a novel spring back model, and this model has shown that it can approximately compensate for up to 60% of the spring back effect, and also addressing the robot end effector deviation, and this has been dealt with a virtual joint modeling. And the third one is like a novel stiffness-based tool-based correction model, which combines the above-mentioned models. It's worth mentioning that the significant findings of these theses have been presented in 5 research publications that I will mention later. To address the first research questions, like a comprehensive review on the limitations of the existing methods have been carried out, and here is the summary. So annealing might be used in this process, which is a heat treatment method, to compensate for the spring back effect. However, there are some limitations due to the cost and the material consideration. And also there are some research to propose artificial neural networks and to, for example, incorporate the particle swarm optimization as an hybrid approach to overcome the spring back effect. However, these methods have some limitations in terms of the training data quality and the interpretability and diagnosis. And also for the part of the tool bus deviations due to the forming forces, there's a lack of resources addressing the modeling of the forces in the incremental sheet forming specifically. So I'm trying to overcome the existing limitations in the current literature. So to start, in the robot forming, the key point is the tool path actually, because you don't have anything else to control. So you control the tool path because it's affect the proper selection of the tool path affects the accuracy of the obtained shape. And the most often used contouring tool path is the Z level and the spiral tool path, which are presented here in figure 6. So for the Z level, it's like some consecutive layers spaced by delta Z, for example, which is the step depths, and it can be created using the presented function. However, in the spiral tool path, which is a helical tool path, and it is better suited for the incremental sheet forming because it tries to distribute the sheet uniformly. So in this research, I'm using the spiral layout, and I considered 3 different profiles as a test cases, which are the truncated cone and the hyperbola and the truncated pyramid. After generating the tool path, it was very important to check the feasibility of the generated trajectory, because later this will be applied to an actual operation, actual robot operation. So to check, for example, the robot singularities and the robot joint limits. So for this, I used RoboDK as a robot programming offline programming tool, and you can see here from the demo. So here I used a Fanuc robot, which will be similar to the ones that will be used in the experimental setup. And I used a predefined workpiece defined created in SolidWorks. And the simulation showed that the tool path coincides with the inner wall of the workpiece. So we can go to the presentation back. So after that, it was the time to perform the numerical simulation analysis. And for the numerical simulation, in order to perform it, you have to go through some stages, starting with the geometry and sheet 2, the material definition and calibration, and the assembly process, as you can see in the figure 13, and setting the boundary condition, and then the meshing process, and after that, the post-processing. For this task, I used the material used is the aluminum with the listed mechanical properties. And here's the results of the numerical simulation process. I used 3 output identifiers to evaluate the results. So, for example, I used the equivalent plastic deformation and the depth, the vertical displacement, and the von Mises stresses. And we can go to the demo, please, here. So this is a practical insight on how the incremental sheet forming, single point incremental sheet forming can be performed using a numerical simulation tool. Okay. Okay, you can go back to the presentation. Okay. So of course there was some errors in the results we obtained due to the spring back effect, which was expected, and this has been done for the 3 proposed profiles that we have, which is the truncated cone and the hyperbola and the truncated pyramid. And in figure 16 here, you can see this is a visualization of the spring back effect, how it introduced some errors. Like for example, there was like 1.1 millimeter errors in the vertical displacement. This is due to the spring back effect. At that point, I used this evaluation metric, like the relative error between the desired depths and the simulated depths. And for example, for the truncated cone, the relative error was 0.5%. However, when comparing like point by point from the desired shape and the obtained shape, there was like a maximum error of 1.4 millimeter, which raises the motivation to do the spring back effect compensation. Just to recap very quickly, until now, like the toolpath definition has been investigated, and the practical insights have been performed to complete the spring back to complete the numerical simulation of the incremental sheet forming. And this simulation study has been published in the International Conference on the Industrial Engineering Applications and Manufacturing. And in this paper, I also proposed the models that I will use to compensate for the spring back and the stiffness-based toolpath deviation. So in order to perform these two models, it's important to extract some data. So from the simulation data, as I mentioned, there is a meshing process of the sheet when it's in undeformed state. So in the meshing process, the meshing generates some elements and some nodes for each particle, I would say. So this node is assigned with a node ID. So in order to track these nodes, I need to store this nodes ID like that are matching my toolpath. And the results of this can be like presented in this table. This is before the deformation. So for each toolpath point, I need to get a specific node ID that I will track later. And for the to implement the stiffness-based algorithm, I need some forces, the action forces of the sheet on the robot end effector. For this, you can see in the left part of the figure 19. This is my toolpath, and on the right side, this is the data generated from the numerical simulation tool, which is the magnitude of the forces. It's worth mentioning that in the figure 19 about the magnitude of the forces, like over time, the forces increases, and this is a normal behavior because the sheet thickness becomes less, which requires you to implement or apply more forces in order to deform the sheet further. So this is the solution actually. If you I presented this figure, I mean the first part of this figure in the problem statement, and this is my solution. So for the spring back effect, like there's like a proposed spring back effect compensation model, and for the toolpath deviation, I will apply virtual joint modeling. And the final result would be like combining these two methods in a sequential manner. So starting from the desired toolpath and get the final toolpath that compensates for both the spring back effect and the toolpath deviation. So for the spring back compensation model, this is the proposed model. It is purely based on the numerical simulation. So you start with the toolpath, that green box, and then you perform the numerical simulation. And out of this numerical simulation, there is a meshing part in which you need to store the nodes ID and the coordinates of these nodes before the deformation. So the key point in this diagram or in this flow chart is these two blue boxes, because basically the idea is I'm getting the data before the deformation, and I'm tracking the nodes after the deformation to get the new toolpath. So the new toolpath can be calculated finally, which here I refer to x prime, y prime, z prime. Just like the compensating for the deviations of these nodes out from the desired toolpath. I mean the original toolpath. So the results of this model has been tested for different materials and for different profiles. For example, here's the presented results for the aluminum. So you can see in the left top figure, like the deviation has deviation due to the spring back effect has become less by 50%. It's more than 50% actually, so it's approximately, and in Y direction as well. However, in the Z direction, it experienced some limitations, but this was only for the aluminum like material, and I will like show how it acts for different materials. I use like 3 metrics to evaluate the results, which are the mean and maximum and standard deviation. And yeah, as you can see, the percentage of mean error compensation in the Z was the least actually for this specific material. So as I said, the evaluation was done in 2 parts. The like for different materials, I tested like for 5 materials and for 3 profiles. Like most of the results were like up to 60%. Like for both the different materials and different profiles. Another key advantages of this proposed model is that if it will not, like it doesn't affect the sheet thickness much. Like if it will not increase or enhance the sheet thickness of the material, it will not impact it in a negative way, I would say. So for example, like in the aluminum, there was like a reduction of sheet thickness by 30%, almost 30%, which is a normal behavior in the incremental sheet forming. And this blue chart, the blue plot, is for the results obtained from the proposed model. It was quite similar to the one before compensation. However, in the copper material, like there was like a slight enhancement in the sheet thickness. This model has been presented in a like published in a case conference that it will be presented next month. So right now we compensated for the spring back. It's time to compensate for the tool path, and for that I used virtual joint modeling as a technique to overcome this problem. And I used like this fun model with this schematic. So in virtual joint modeling, you extend your kinematic chain with virtual spring. For example, the joint would be extended by only one degree of freedom spring, and for the rigid for the elastic link, it will be presented by a rigid link plus 60 degree of freedom virtual springs. That's why like the transformation for the forward kinematics will become like more like complex like by adding these virtual springs. So the basic idea behind the VGM is to obtaining the classical stiffness Cartesian stiffness matrix, which can be obtained out of the like the Jacobian matrix, and here it's computed numerically. Yeah, it's worth mentioning that also like this K theta, which is the aggregated matrix that combines the stiffness matrices of the joints and the stiffness matrices of the links. It will be like out of size like 42, because we have here like 42 virtual springs, and the like principal idea behind this is the Hooke's law in a simple words. So once I obtained the Cartesian stiffness matrix and I got the reaction forces out from the numerical simulation, I can basically calculate the deflection. So the results of this model can be presented here in figure 28, which is the deflection map of this toolpath, and we can see it more precisely in the demo. Yeah. Okay. If you can zoom in a little, or just make it bigger. Okay. So in this demo here, I'm using like Robot DK and MATLAB. And the right side, I'm solving for the kinematics and the inverse kinematics of the toolpath that I'm trying to generate. And in the left side, I'm calculating I'm applying the virtual joint modeling, and at the same time calculate the deflections. If you can go please at the end of the video, yeah, somewhere here. So yeah, at the end of this toolpath, the model will generate these deflection maps that will be used later for the compensation. Okay, you can go to the presentation. Okay, here like this, okay. Here like x prime and y prime and z prime we obtain from the spring back effect compensation. So here I'm getting the new tool path out of these like compensated tool path from the spring back effect. And you can see the final tool path that should compensate for both the spring back effect and the tool path deviation is presented here in figure 29. So this flow chart explains these VGM tool path correction method. So as I said, you start with the tool path and then you perform the numerical simulation to generate or get some intuition about the reaction forces that the sheet can apply to the tool. And at the same time, you start with the tool path solving for the forward and inverse kinematics to perform the VGM model. So once you arrive to this block, you have the Cartesian stiffness matrix and you have the force and torque sensor measurements, so you can get the deflections. And again, using the desired tool path with this deflection, you can calculate the new compensated tool path using simply this equation here. This work has been accepted for publication in the International Conference on Mechatronics and Electrical System, and it will be presented next month. So yeah, as you can see here from the obtained tool path, there was some abrupt changes and sudden changes in the tool path. This has been dealt with applying different smoothing techniques. Like for example, I used the sliding window and Fourier transform and the Kalman filter, Kalman smoothing. So to conclude, like this research first provides a comprehensive review on the incremental sheet forming and just to address the first researcher questions. And after that, I provide practical insights to perform the numerical simulation of this specific application. And a novel offline spring back effect compensation model is proposed, which is purely based on a numerical simulation. And this answers the second research questions. And after that, the offline stiffness-based model was proposed, which is based on a virtual joint modeling technique that addresses the last research questions. The future investigations would be dedicated to first to check or extend the spring back effect to compensate also for the reduction in the sheet thickness, and also to see the experimental validation of this work, like how this model would act in the experimental setup, and also to incorporate some feedback controller or sensing controller, model predictive control, for example, to this work, to see how it can be done in a real time, in a real time adaptation way. And finally, there's ongoing research in the double-sided incremental forming, to check how these models would perform in a co-manipulation way. Finally, this is the publications related to these works, and that's all from my side. Any questions?
Well, Boris?
May I ask a question, Lisa?
Please.
Thank you, Walid, very much for your impressive talk. It's just that, from what I understand, you've shown this trajectory, right, which is a conical shape, right?
Yeah.
And so my question would be, the algorithms you've developed, both for modeling and for estimation and thickness correction, how scalable, how transferable are they to other trajectory shapes, to other milling or forming velocities, and just to to the specifications of your desired shape, the final shape of the part that you are making? Because from what I understand, are they customized or are they more or less general?
No, in this case, it's a general approach. I used only these three profiles as a test cases, but once there is like generated toolpath or trajectory for a certain shape, like I mean the model will not mind to do the compensation because it is based on the numerical simulation. The only problem might be in the numerical simulation process when you try to deform the sheet to get this desired trajectory. But the model is capable of like getting the the deflections, like the nodes deflection from of the sheet, and it has previously the desired toolpath, so it can compensate it.
And also you mentioned different materials, right?
Yes.
Which is fair enough. But then there can be different finishings on the materials, and just like in the trajectories you've shown, obviously you will need to pre-plan the number of layers, how deeply you go in each layer, right? But also I would imagine if you have non-symmetrical shapes of the trajectory, right, which may or may not have sharp or sharpish corners and bends. So how does material and trajectory shape affect the algorithm? Can you briefly summarize, please, in terms of how many layers you need to make, how quickly you need to go between each layer, and as such?
Okay. So for this part, I mean the depth between the layers was set to 3 millimeters, and I believe if the distance between the layers can be like less than that, it will have like better results because like there will be like much nodes in the meshing process. So when I'm trying to match from the desired toolpath, I will find a node near to my toolpath point if there are like multiple nodes presented in my sheet. The second point about the complex geometry, actually the advantages of the incremental sheet forming, it can do the shapes that has undercuts or the complex 3D geometries, but I didn't experience like simulation of this shapes in this part, but I'm trying to like go further and test one of these sheets.
Okay, thank you. If others have questions, please go ahead.
Thank you. Well, other questions? No? Please read the assessment.
Finally, the assessment from supervisor. The aim of the work was to optimize the robot trajectory in the incremental sheet forming process. The work is related to multidisciplinary research at the intersection of robotics and materials science. During the work on the theme, student has demonstrated high involvement, initiative, and creativity. As part of his work, he delved into the understanding of the technological process of incremental metal forming, the behavior of the material during and after processing, and the behavior of the robot during the forming process. To conduct research and